Thank you very much. So first, I'm very happy to talk these special occasions. And when I was asked to give this talk, I feel very honored and I'm very happy about it. But I think since this is an occasion for the Maxim Kontsevich, so I feel I need to talk something about a kind of dream or something very much promising in the futures. But unfortunately, for years recently, somehow we are more concentrated on something like writing down the foundations in very much detail, rather than pushing the applications ahead. And it seems that it is not so much Maxim's style mathematics. But since we spend so much time to write up these details, so I feel that there is some excuse to write that kind of thick and heavy things. And these virtual techniques are first invented by several people, including myself and my collaborators like Ono Ota, to study this, to study the foundation of global fitness theory and the Fourier homology, like a pseudo-harmonic curve. But then I feel that the technique should be somehow related to some people try to use in the quantum field theory physics. So if it really can be used to study some quantum field theory, so it's a good excuse to write this thick volume. So that's something I dream. So, but then the talk, so in application side, what I am going to talk, it does not go so much beyond what I talked in several other occasions. But I want to explain more about this foundation things. And in this talk, virtual fundamental class appears for some simple moduli space of constant maps. And this is somewhat better for people who want to understand what is virtual techniques. Because if you start learning virtual fundamental classes, usually it is about pseudo-harmonic curve, and you need to start learning nonlinear PDE, and a lot of functional analysis is rather complicated. And if you learn a lot of functional analysis, then this story starts. But fortunately, what I am going to talk does not use any nonlinear PDE or functional analysis. It's just about finite dimensional topology. So there are some people who like this kind of virtual things, but do not like so much nonlinear PDE. So for those people, maybe to explain this particular case might make sense to understand what this virtual technique is. Okay, so since the quantum field theory is in my title, I just say a few words about it, and I'm not at all a specialist. So when you run quantum field theory, we learn that there are a lot of integrals, like Feynman integrals, not yet a path integral, but still Feynman integral it can be infinite in many cases. And what physicists do is just to somehow regularize to this Feynman integrals and to get some finite number. Usually, for example, they cut at some energies, so it's your integral. So many times this infinity arises from diagonal. So you cut energies, and this infinity is a bit get better. And one important point is to kind of regularize as much symmetry as possible you keep, and that's something a similar problem we meet. And then we have this kind of system of numbers depending on some parameter, say epsilon. And when epsilon goes to 0, you get a kind of something which you want to really calculate. But in certain cases, especially what I heard from physicists is that in the case of topological field theory or some other cases, there is something called a supersymmetry. And this supersymmetry implies that even if you kind of first kind of perturb it a bit, but this final result is independent, and when epsilon goes to 0, so even if this diverges, epsilon goes to 0, you can still get some finite things. That I think is one of the role of supersymmetry is useful. So I want to say some very simple example, but interesting example. It's about Atiyah-Zinga index theorem. So you start from this elliptic operators, and what you want to calculate is a difference of dimensions. Dimension of this, so E1 is a vector bundle. So this is an infinite dimensional space of sessions and the infinite dimensional space of sessions. And this difference, And of course, this is infinite. And you want to, then what many people do is just to take this trace of e to the power minus epsilon p star p. When epsilon is 0, this trace is just this. And when epsilon is 0, this is just this. So you just take a difference. And of course, this when epsilon is positive and p is elliptic, this difference is finite. And what this supersymmetry means, in this case, that this difference is actually independent on epsilon. So you can go to epsilon equals 0, then you get something well defined, and that's of course index of an elliptic operator. And that I think is this particular some example of this kind of story. But this is a linear story, so something non-linear version of this kind of thing should be, I believe, is topological field theory. So I want to talk something similar but different things. So this virtual technique started to, for example, main thing is try to define Gromov-Witten invariant. And many invariant of topological field theory is some kind of intersection theory. So intersection theory, you can see the following things. You have two cycles on M, and we assume that, this is plus, I'm sorry. The plus of degree is dimensions. So in a lucky case, you take these intersections and to calculate the orders. And this one should be an intersection number. Everything works fine. But of course, this works only in case they intersect transversally. And if they are not transversal, then you take this, so this is the infinite number. So you can just perturb them so that you get the finite numbers and it is defined. But sometimes one cannot simply do this. That's and in algebraic geometry and differential geometry, there are some difference between around the intersection theory. So in algebraic geometry, intersection of cycles is always defined. And if the intersection is somehow finite order, then it is always positive. And the kind of negative intersection occurs only in case some component coincides. But in a differential geometry, there is something different. What's different is that in algebraic world, there is no manifold has a boundary. So complex manifold has a codimension 2 strata only. So this is why this intersection number is always very defined. But in a differential geometry world, intersection number may not be very defined because the cycle, not cycle, but the kind of manifold may have a boundary or corners. That's one reason. And also, even in the case this intersections is finite order, but you may still have a cancellations, the sign, plus and minus. And in algebraic geometry, mostly the sign is always plus. So, but then somehow how to handle this sign and how to handle this non-well-definedness of the intersection number, these 2 points is actually some kind of a main thing we need to work out when we do this virtual techniques. So write up the sign correctly and how to handle this non-well-definedness of the intersections. And in a kind of topological field theory, the situation I feel is rather closer to differential geometry than algebraic geometry, because one of the important features of some topological field theory, especially the case of Frey homology, is you try to define various numbers or various quantities, but they are in general not well defined. It means that if you perturb or if you kind of modify the problem so that you can count something, the number you get itself is not well defined. And something you get well defined is only you define everything as a whole, and everything is well defined only up to homotopy. So that happens very much repeatedly in recent years in this business, in simplex geometry or in some related fields. So this is the reason that this kind of differential geometric style of this intersection theory is kind of related to these problems. Okay, so this is what I want to say. So what I want to say about this topological field theory is we need to define various quantities which is not well defined, and we define something only up to homotopy equivalence. And but then what we do is just to kind of we have some bad intersection theory. So we want to perturb so that we get well-defined numbers. But then its number depend only on this, depend on epsilon. It's a parameter you perturb. And the number itself may depend on epsilon. But then there is some supersymmetry. Then this is dependent on epsilon up to some kind of homotopy equivalence. So how to handle this kind of situations in general is a kind of theme of this virtual fundamental chain techniques. But rather than going to that directly, I want to explain one particular example. So making system of intersections of various chains consistently to obtain a system of numbers. So the main issue is that each numbers are not well defined individually. So what you need to be careful is not study each kind of one problems and to get numbers individually. You need to study infinitely many problems at the same time so that everything you do is consistent. And what I mean by consistent, how to make it consistent, is a kind of a main headache for these virtual techniques. And that's kind of, yeah, so yeah. Okay, so this is what these virtual techniques are doing. Yeah. And I will explain the case of constant maps. And that is something, and also the case of the maps from border Riemann surface. So Riemann surface with boundary. And as I said that you don't need PDE, but you kind of finite dimensional topology. But still you have some systems of non-transversal intersections which are interrelated to each other. So I just want to start explaining which kind of intersection problem you meet. And then I want to explain some kind of general machinery, how to handle this kind of system of intersection problems so that you get a well-defined structure. So the case I would explain is this Chern-Simons, but I want to start a very simple case, simple things. That is a wedge product. So let M be a manifold, and we consider a triple power of M cube. Then you have projections to first and second factor. It is M square, and the third factor, this is M. So this is square. This makes things a bit nonlinear. In a sense, like a linear partial differential equation, you have a M square and M, but you have a M square and M, so you have just linear things. But this is a kind of multilinear. And the thing we use is this diagonal, so small diagonal, M itself, X is X. You have this M cube. And this kind of diagram is a kind of correspondence. And what this correspondence gives you is a wedge product. Suppose you have two differential forms. So lambda M today is always a differential form. You have a smooth differential forms, a pair of smooth differential forms on M. So you get H1, H2, then you can just take exterior product. You get the differential form of M square. Then you pull back by this map. And you take this distributions. It's a Poincare dual diagonal. So this is M is n dimensional. This is 3n dimensions. And this diagonal has n dimensions. So this distribution has a degree 2m. So you can wedge these distributions, and you take integration along the fibers. And it is easy to see that what you get is this usual wedge product. So this just means that you take these particular distributions, it gives some kind of Schwarz kernel of the wedge product. So this is and this product is well defined. There is no infinity yet. But for the purpose of later use, I want to make these distributions T diagonal a bit smooth, so to regularize these distributions. And the data we need to do is the following things. So this diagonal is somehow, this distribution is not supported on an open set. It's just on a closed set. That's why it is not smooth and distributions. So we take this open tubular neighborhood of the diagonal, and you have this projections of tubular neighborhood, and you take normal bundle of this diagonal in M cube, and you put back on this U. So you have this U and E, and you have a natural canonical section S. It's just a tautological sections, because U is an open subset of this normal bundle itself. And the property is that the zero set of this tautological section is just diagonal itself. So in place of studying diagonal, we consider this triple, U is a tubular neighborhood of the diagonal, and E is a kind of normal bundle, and S is the topological sections. So this triple is a kind of simplest, very simple version of Coulombic structure. And actually, in this talk, the Coulombic structure appears rather in this simple way. Sometimes, in general, we have only locally this kind of presentations. You have a pair of spaces, bundles, and the sections, and you represent your space as a zero set of the sections. And in general, you need to do it locally. But in this simple story of constant maps, you can do it globally. So you have just this kind of triples. And the reason that this is better is that this map from U to M3 is some margins, MQ with some margin, because this is open set. So then we want to see that this picture as a diagram like this. So you have this disk with 3 marked points, and you have a map U, and the partial differential equation in this case is very simple. It's not even a differential equation. The condition is just U is constant maps. So you consider the moduli space of constant maps from the border-Riemann surface with 3 marked points. And border-Riemann surface with 3 marked points is, of course, no moduli. And this U, constant map, is parameterized by M itself. So the moduli space is very simple, that M itself. And that is exactly this diagonal. And you have this evaluation map. And this evaluation map, of course, is this X go to X, X, X. So that's a simple case. So now, I want to go to the next case. So you can increase the marked points, but in place of this increasing marked point, you put one loop case. And the simplest case is this guy. So you have this disk with 3 marked points, but you put the conditions that the first and second marked point go to the same point. Of course, this is rather ridiculous because your equation is U is constant, so this is always satisfied. But let us consider this as a kind of conditions. Then the moduli, so your moduli space is this singular annuli, so annulus with one node. And you have a pair of this moduli space and a map U to M that is a constant maps. Of course, the moduli space, so that then you can regard this one as a foreign fiber product. So you have a diagonal. Diagonal is a moduli space of this disk with 3 marked points. But then you equate that this G1, G2 go to the same point. This means that you take another M square, and you take a fiber product, and the first factor goes to X, 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 and the second factor goes X, Y, and X, X, Y. This means that you equate the first and the second go to the same place. So you take this simple fiber product, and of course this simple fiber product set theoretically is again equal to M. It's just a constant map, and the source has no moduli. But what's wrong about it is that this fiber product is not a good fiber product. Its dimension is not correct. I mean, this dimension should be 0 dimensional, but it has an M itself because the intersection is not transversal. So you can write, you can kind of rephrase it in the following way. So this diagonal as a current is equal to this, the x, y, z is a M. So you have a delta functions and dx, dy, dz. This is 2n forms. But then this M square is just you equate x is equal to y, so you have a delta x minus y dx. So you want to take intersections and you want to count the number. The natural thing is to take a weight of these two currents and integrate. But of course, this is not well defined because x minus y, delta function of x minus y square is not well defined. So you try to do this by some kind of ways, then you get infinity. And how to kind of remove this infinity is something like related to this intersection theory. And if you think a bit about the intersection number of this delta m and m square, you will see that this is Euler number. So somehow you want to regularize these integrations to get Euler number. So this is the kind of first part of these things. And so now in place of this taking this diagonal itself, you take this open neighborhood. So you take this U, the tubular neighborhood of your diagonal, and you take E, that is obstruction bundle. So you take this triple in place of this taking M itself. So what's nice is that this U, if you take this U, it's a neighborhood of the diagonals, then you can take this fiber product. It is just well-defined fiber product. So this is I think n-dimensional. No, 2n dimensional manifold, and E is rank 2n bundles. So you have a 2n dimensional manifold and rank 2n bundles and S, and so this manifold is 2n dimensional, and this is rank 2n, but S is something singular, so something non-transversal. So that this zero set is again this M itself. So you can cook up this fiber product naturally, and E also, but S is not transversal to 0. So that's the reason your space is long. So still, what's nice is that you can take this fiber product. So by increasing somehow your space like this, you can always make your fiber product well defined. And you can make this picture a bit smaller. So this S is not transversal to 0. So but then you can just reduce this. So the cokernel of this S is actually tangent bundle. And then since this is a finite rank, so in place of this taking 2n dimensional manifold, that is something like a neighborhood of M. You just take M itself. So you replace this triple, this guy and E and S by a bit smaller one. So you get M tangent bundle 0. And this is our triple. And what's wrong is that this S is 0, so it's not transversal. But you can turn this 0 something like a non-generic sections, and you get Euler number. So that's the story. Okay, so now so this is in this particular things. But then this thing is a boundary of some other moduli spaces. So you can just take this general annuli. So in place of taking this moduli space just at one point, you take moduli space of annuli and a constant map again. So now we consider this moduli space M1, 1, 0. So this 1 means that I'm sorry, this is 0. I'm sorry, this should be 0. Annulus has genus 0. Sorry, this is wrong. So you have a genus 0 Riemann surface, and you have this 1, 0. You have a 2 boundary component, and one of them has just 1 marked point, and the other has no marked point. So that's this. So this is M0, 1, 0. And you have a parameter U, that is M. So you have this moduli space. And so this moduli space is actually, you can calculate very easily. So this is 0 again, I said. So moduli space of annuli with 1 marked point is exactly interval. So you have this interval, and this moduli space is interval times M. And this is a very nice, smooth moduli space, but you are not supposed to regard this is a transversal moduli space. And the equation that U is constant is actually degenerate equations. And in this case, you have a obstruction bundle that is H1 of your annulus. And H1 of your annulus is rank 1. And you have this kind of tangent bundle coefficient of H1. That is our E. So you have this space itself, but you have this obstruction bundle. So the triple you have is this 0 interval times M and tangent bundle and 0 sections. So this is actually this triple, which you get in this case. And what you can observe is that that you go to one of the boundaries. So you have a boundary of this moduli space of annuli with marked points has 2 boundary points. And one of the boundary points is just you get here. And the other boundary is something here. So this is the case when this inner circle shrinks to a point. And this boundary appears actually in a talk by Costellos and also Mohammed Abzai. So it appears in a similar way. But anyway, so you have a 2 boundary of this moduli space. But then on this first boundary, what's good about this is if you consider this boundary, then the pictures, you have this moduli space of annuli is this interval times M and tangent bundle. And if you consider this, so you get by taking fiber product, you obtain this similar moduli space. And this is exactly coincides match with this. So the story is something like this. You have a kind of a moduli space of genus 0, 2 boundary marked points, and 1 boundary marked point. And then you put using H1, you put obstruction bundles. And you go to the boundary of this moduli space. You have the same moduli space as this fiber product, which came from genus 0 with 1 boundary component. So what I want to claim is that this is a completely general picture. So you can take I'm sorry, yeah. Yeah, the second boundary, there is a way to handle this second boundary, which I think is Costello mentioned a bit. In our particular case, you can just assume that the Euler class of M is 0. Then these 0 sections have a chain which bounds it, and you can eliminate this boundary using these chains. But that's not so much things I want to talk today. So now we can completely generalize these pictures in an arbitrary Riemann surface of arbitrary genus and arbitrary boundary components and arbitrary number of marked points. So we consider this M, G, K1, K2, blah, 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 KL. So that's a kind of moduli space of bordered Riemann surface. And this Riemann surface is supposed to have a genus G, and we assume that it has a L boundary component. And on each boundary component, you have a K1, K2, blah, 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 KL marked points on S1, which respect this cyclic ordering. So we consider this moduli space, and this is actually a manifold with corners. So you get manifold with corners like this, and you consider this plus constant maps. So the moduli space you get is this one. So this is I think this is not an obifold. This is not a manifold, but it's an obifold. But you have a kind of at least smooth obifold, and a smooth manifold, and you have obstruction bundles, and the section is 0. So you have this triple, so that you have one obifold and one vector bundle on it, and the section is happen to be 0 in this case. So you have a system of this triple for many Z, K1, blah, 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 KL. And what we know is that, but then I want to say something about this, because this one is a good manifold, but you consider a variation map, then a variation map just goes to diagonals, so it's not a submargins. The problem is, if this is not submargins, you cannot take fiber product. I mean, as I said, that in the case of this, going to genus 0 to genus, 0 loop to 1 loop, you have to kind of equate 2 points intersect. And you do not extend this moduli space of 3 marked point disk. This equation is not good equations. So to make it transversal, you need to make this a variation map to be a submargins. That you can do easily by just replacing this M to replace M to a kind of tubular neighborhood of this small diagonal in a big product. And you can just take normal boundary and pull back. So you can just extend this a bit. This is 0 is not correct. This is the tautological sections. I'm sorry. This 0 is not correct. This first factor, the map is 0, but second factor, you take this tautological map. So that the 0 set is again the same thing. So you have this a bit bigger modular space. You can just use this and this. And they are somehow equivalent as a kind of structures. So what we get is that you have this system of modular spaces together with this variation map to the power m to the power k. K is a sum of ki. And what's nice of this picture is you go to the boundary of this modular space. It means that you have a kind of bordered Riemann surface, you have some singularity. And then these singular things, in the case of this annuli, can be written as a fiber product of something you get in an earlier stage over M. So this is the general picture you have. You have a kind of, for each alpha, A is some partial order set. In a special case, A is a combination of the genus and K1 blah 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 KL. You can order it by something like a lexicotic order. And then on this partial order set, you obtain this triple. U alpha is an obifold with corner. E alpha is a vector bundle in obifold sense on this. And S alpha is the sections. And its 0 set is your moduli space. So you have these sections of this triple, or various alpha. And you have F alpha from U alpha to this n to the power n alpha. And this is can be assumed to be submargins. And what's nice is that you take the boundary of this, then it is a union of various fiber product of something you get in earlier stage. And its fiber product is taken by using a part of this evaluation maps. So this is in the particular case of this system of the pictures, in the case of constant maps. So this is, what's nice is that it is rather easy to cook up these constructions. You have this modular space of Riemann surface, and you have just M, and you can just take this neighborhood of diagonals. And if you want to do this in a more general setting of kind of, in a case when you have a pseudo-harmonic curve, then you can cook up this kind of pictures using nonlinear PDE and a lot of functional analysis. But here, you're just finite dimensional topology, so you can just get this. So the only thing you need is to understand what this degenerations of border-Riemann surface occurs. So that's also, but anyway, so this is a kind of quite general situations. And this occurs, I think, in many stories, especially this occurs in pseudo-harmonic curve. But in this case, pseudo-harmonic curve is very simple, just a constant map. So then what is a virtual chain technique is the following. You start from this kind of systems. You have this system of orbifold, system of vector bundles, system of sections, and these triple are related to each other as a boundary by fiber product. Then the virtual technique says that you can kind of systematically perturb all these modular spaces so that it is kind of consistent to this fiber product restriction of the boundary. And so that is what this virtual technique do. And once you can do it, you get some system of numbers. And this system of numbers is actually kind of Chern-Simons theory of your manifold. And I say that this the system of numbers you get actually depends on the choice of perturbations. However, you can cook up some cobordism argument so that if you make these perturbations consistently for all alpha, then what you finally obtain is well defined up to certain homotopy equivalence. And what I want to emphasize is that this is a kind of complete general theorem. So you can just you have this kind of general situations. Then you can always perturb everything in a consistent way so that you get something well defined up to homotopy. So this is a kind of a general procedure, and this is what this virtual technique are doing. And yeah, actually, so the virtual techniques, I think there are several group of people, including myself, ourselves try to write down this in details. And unfortunately, whenever we write down the details, the totality is rather thick volume. And I feel that it seems impossible to write down in complete detail less than 500 pages. But what's good is about this story is even it is heavy, but it works always. So I mean, it means that you don't need any kind of special assumptions. So whenever you have this kind of things, it always works. So the good news is that something like this kind of things you can use without understanding, because if you need delicate conditions, then you need to understand why this works, and you have to be very careful before you use it. But my propaganda about this virtual technique is that this is free, so it works whenever this situation appears. So you don't even need to read this kind of complicated things, and you can just use it because it works always. So what I want to do in the rest of my time is to state this theorem a bit more precisely, so that you can use it. And something we are doing for this year is somehow to write down the statement which you can use without knowing the proof, because I'm pretty sure that not so many people want to read the proof, because the proof is something like similar to what you learn in a third or fourth year undergraduate course of manifold theory. And there are some people like Dominic Joyce, and I think Dominic Joyce wants to write the story as close to the theory of schemes and stacks. But I am rather differential geometers than algebraic geometers, and so I want to make it as close as to theory of manifolds. So it has an advantage. I think smooth manifold is easier than schemes. So, and what I want to explain the rest of the time is very much similar to what you learn in undergraduate course of manifold theory. So I want to explain what is integrals and what is okay. So now I want to do it what is a bit more precise. So you start from this situation. So I want to consider individual space. You have a triple U, E, S. So let me remind you that U is an orbifold, E is a vector boundary in orbifold sense, and S is a sections. And maybe only assumption is S inverse 0 is compact. It may be very singular, but you assume it's compact. U may not be compact. You have a kind of open neighborhood. And something you need some orientability. And also you have a F from U to M. M is a manifold. And this map you assume to be submargins. So that's the situations you work with. Then the theorem is you have a sheaf on U, which you can associate to these things. The sheaf of set and it has the following properties. So I want to explain which properties this sheaf has. And this sheaf is a kind of a sheaf which parameterizes the way you perturb your moduli space. So you have some sheaf which parameterizes the perturbations. So what is the first property of the sheaf? The first property of the sheaf is the following. So you have this triple. And suppose H is a differential form of with compact support in some open set omega of U. And suppose you have a sections of your sheaf on omega, on omega. Then you can define push out or integration along the fibers of these differential forms. You get somehow differential form of M, but it depends on epsilon. That is positive. So this means that something I want to do is just to push out these differential forms on this space to M. Of course, you have a differential form on U and F is some margins, and compact support smooth form by some margin you can always push out integration along the fibers. But the space itself is not U, but it's a kind of zero set of S, and zero set of S is extremely wild, so you cannot push out your differential forms on this wild set. But you have some parameter space which regularizes your zero set, and if you fix this element of this parameter space and fix epsilon, you can push out the differential forms. And the typical situation, it's easier situation, this push out the following form. Suppose that this S is transversal to 0. Then S inverse 0 is a smooth manifold, compact smooth manifold, but F may not be some margins. But then you can still push out differential forms, but what you get is a current. And the property of this push out is that if you go to epsilon goes to 0, then this push out is a current, which is the push out of H. So you can write it in the following way. If you have any test functions, smooth forms on M, you put back on these forms on U and you integrate over this zero set of S. Since this is transversal to 0, this makes sense. This integration is equal to this push out and wedge sigma and take limit epsilon goes to 0. So that's a property. So something we want to do is just this is the smooth form which regularizes the push out of this differential form on S inverse 0. So that's something we do. But of course, in general, zero set of S is not a smooth submanifold. It is a singular space. And you cannot expect that this limit converge other distributions. In a case, S inverse 0 is wild. So it can be a very wild things. And I don't want to go to epsilon. I don't want to study epsilon 0 itself. But it kind of very close to 0, you get some number. And this number may depend on epsilon. This number may depend on these perturbations. But you still get something. So that is what these sheaves do. But then there are several other properties of this sheaf. The next property is this sheaf is, I'm not so sure about this terminology. This is soft. The soft sheaf means that you have any closed set on omega, and there is kind of restriction of the sections. This is always surjective. So it means, so why this is good? So because this property you can use to prove the existence of the sections. What you want to do is just you want to construct this parameter of this section of this sheaf systematically. But then this is soft sheaf. It means that you have a kind of, you define something over there, you can always extend to get something you want. So this is the soft sheaf. Moreover, you can define a partition of unity for this sheaf. And this sheaf is unfortunately is not a sheaf of groups. It is a sheaf of set. So, but it's kind of a affine type thing. So you can define partition of unity, and you can define these extensions. So this is the main thing we can use to prove the existence of this kind of perturbations. And so since you are working on these integrations, the main theorem should be Stokes theorem. So it's something like we learn at the end of the course of manifold. It's Stokes theorem. So what this Stokes theorem means that suppose you have this triple UES, and suppose this U orbifold has a boundary. It may have a corner, but it may have a boundary and corners. So you restrict this H to this boundary of U, and you restrict this. So there is a notion of this. You have a restriction map of this section of sheaves to the boundary. You restrict these sections to the boundary, and epsilon is the same. And you just push. So you use this data to push out. But this is a kind of D of this push out, and push out of this D of H. So maybe minus. The sign I need to work out. So this means that, that if we go to the boundaries, and this is related to this. So this is actually a Stokes theorem. And to make it clear, I want to explain one special example. So suppose that M is just a point. So in this case, push out, you get a number. So it's a usual integrations. So in place of writing this, I just want to write integration. So you can integrate H of this space U with this perturbation data. This is the number depending on epsilon. And this integration satisfies this usual Stokes theorem. If you integrate the boundary, and it's equal to this integration of D of H. So this is the Stokes theorem. Now, the other thing I want to explain is something like a Fubini theorem or composition formula. So what is Fubini theorem? Fubini theorem is something related to how these integrations behave by product. And as you see that the story I want to cook up is you have a system of spaces so that one boundary of one spaces is described by fiber product with other spaces. And something what this virtual technique do is you start from this geometric situations and you rewrite all these geometric relations systematically to algebraic relations. So this means that so the equations we have on our spaces is something like this. Boundary of U alpha is a kind of sum of fiber product. Right? So I want to rewrite this equation something like a D of M equal to M. So this is a kind of algebraic relations among these operators. And this is geometry. So to go this to this from this is a kind of main thing about this virtual things, chain level virtual technique. But then you see that here you have this boundary. So you can kind of translate this boundary of your space to this operator D by using Stokes theorem. So this part you have a Stokes theorem. But on the other hand, the other part is a fiber product, and you want to relate to the compositions. So that is the role of this Fubini, or this push-out Fubini theorems. So I want to state this Fubini theorem a bit more precise. So we are in the following situations. Suppose you have a UI, I is 1, 2, U1, U1, UI, EI, SI, I is 1 and 2. And you have a map Fi to M. So you have this map. Then for these systems, you can take fiber product. As I say that this F1 and F2 are submargins, so you can just take this fiber product. Just space U is just fiber product, and you can pull back these sections of obstruction bundles by this map. So you get UES, so you have this U. And also you have this, your sheaf has a kind of compatible of this fiber product operations. So suppose you have this, so you have this S1, U1, this is a sheaf here, and S2, U2 is a sheaf here. So you pull back this sheaf by this pi 1, pi 2, and you have this sheaf here, this is related to the structures, and you have this natural operations. So the sheaf operation means that you have a series of maps which are compatible with the restrictions. So you get this, you have two perturbation data here, then you get this product perturbation data. So that's always possible. And this, what Fubini theorem says are following things. Suppose you have this H1 or differential form on U1 and H2 differential form on U2. Then you do the following two things. And also you have this S1 and S2 on U1 and U2. So first thing is that you push out differential forms by this using this data. You get a differential form of M. And you push out using this S2 and you get differential form on M also. You take the wedge product. This is smooth differential forms on this finite dimensional manifold. And you integrate. So this is this second formula. And the first formula, you have a differential form here, you pull back here, and you have another differential form, you pull back here, and you take wedge, and then you use this product perturbation data, and you integrate by this product perturbation data. So the Fubini theorem says that this is just equal. And if you think the very simple case, like E1 and E2 is 0, then this is exactly what this you can prove by Fubini theorem itself. So you have this Fubini theorems. Now, this is Fubini, and I want to say that this is related to composition formula, something like a composition of smooth correspondence that I want to explain. So in a usual situation, you have this U, and you have F2, but not only F2, you have always F1. So you have this triple, and F2 should be submargin, but F1 may not be submargin. So this one is something like a C infinity version of the correspondence. So we use this correspondence diagrams. I want to write script U. Then once we have this correspondence diagrams, you can associate a map from differential form of M1 to differential form of M2. It is very easy to do so. You have H here. You put back by F1. This is free. Put back of differential form is very easy. You can put back differential forms here on the U, but then you prepare this data, which you integrate this on this U. Then you can push out using this. You can put back and push down. You get this correspondence. So once you are given this correspondence diagram together with this data script S, then you get this this continuous map of correspondence. So that is something what this virtual things give in general. Then you can compose the correspondence in a following way. You have this correspondence from M1 to M2, and you have I'm sorry, this is 3. You have a correspondence from M2 to M3. So you take the fiber product of this side. This one is submargin, so you can just take fiber product here. Then you can use this fiber product, and then you can compose this, you get this map, and you compose this, you get this map. This is the composition of the correspondence. Of course, it's usual. And then you have compositions, and also since this one is again submargins, you can just use this product of this perturbation data, and you get this perturbation data here. It is a compositions. And what Fubini theorem says in this case is that you take a correspondence of this map associated to this correspondence. It's just a composition of this and this. You can just this one and it's equal to this one. That's what this Fubini says. So your Fubini theorem immediately says that this process associating linear map of differential forms to smooth correspondence is compatible with the process to compose the maps. It's a completely factorial. So this is this Fubini theorems. So you have this Stokes and Fubini, and you can use this existence theorems. But then I want to claim another last property of these things. So you have this again triple UES and script U. Script U is this triple, and U in general has a corner. And suppose that you have a boundary and the corner. So this is the kind of picture. So then this boundary can be decomposed into union of finitely many components, and each two components intersect along the corners. There might be a higher dimensional corner, but kind of codimension 2 corner, they intersect. And this final property is the following. Suppose you have this data which describe perturbations on this boundary 1, boundary 2, boundary 3 individually, this, and suppose that they coincide on this codimension 2 corners. Then you can extend this system to the whole systems. And let me remind you that this sheaf is actually a soft sheaf. So if you extend this system to a neighborhood of the boundary, then actually you are done, because it is the open set. So you have a kind of closed set, and it extended to its open neighborhood, then it extends to everywhere. But this boundary itself is not an open set. So you need a bit some property to extend this system to a small neighborhood of this system of the boundaries. But you can always do it. This is what this theorem says. So I believe that these are other kind of these claims are kind of a simple thing to understand. I don't want to explain what is this sheaf itself, because you don't need to understand what it is. It is not so much complicated.
But empty, yeah. Sugar not empty, isn't it?
Yeah. Of course, yes. Yeah. Yeah, so not only soft, but also germ is non-trivial. Yes, that's important. Yes, you're right. So you know that all these properties, then kind of what I claimed about this, you can do this perturbation in complete generality. It just follows from all the properties I just explained. So this is the situations you start with. You have a system of the triples, some orbifold, vector bundles, and sections. And what you know is that this is parameterized by partial order set, and you go to the boundary, it is a fiber product of something you get in an earlier stage. So now, something we want to do is just to associate to associate this S of alpha for each of this U alpha so that it is consistent with this identity, with this kind of identities. And you can do it just without knowing any proof, just all the things I claimed. You start from these inductions. So your alpha is parameterized by some partial order set A. So you start something smallest. There it doesn't have a boundary. And Maxim says that this is non-empty. So if it is non-empty at one point, the softness implies that the global thing is non-empty. But then you go to this induction hypothesis. So you want to construct, so suppose you have this construct S of alpha or any beta, which is strictly smaller than alpha. Then you want to look this diagrams, and you take this boundary here. You have this S of beta 1, S of beta 2 everywhere here. And actually, I didn't say that somehow this kind of stratifications are designed so that these descriptions are automatically compatible in codimension 2 corners. So then the assumptions that everything which is each boundary component well defined and the codimension 2 corner consistent extend to the interior is satisfied. So you get this system of this data of perturbations. So that's a kind of free. You can use those properties I claimed. So now you can use this data to integrate differential forms which you have on M. You can just put back the differential forms to integrate. So you get a kind of a system of numbers for each alpha, or a kind of system of linear maps between differential forms on each alpha. So you get this huge family of operations. And what's good is that, as I said here, you have this equality between boundary of moduli space by other moduli space via fiber product. But then you can use the Stokes theorem so that this one gives just the D of this operations. And this composition formula means that this second one is just a composition of these two morphisms. So you get this equalities you want immediately once you have this cook up these systems. And the typical example is if you just restrict to this genus 0 and 1 boundary marked points, then you get infinity structures immediately from these constructions. But that's you need analysis because, you need shadow homework curve. But in this particular case of this constant maps, you have this system of constant maps. So you get this system of some operations of differential forms on M. And that basically is the Chern-Simons theory. And I think this satisfies certain locality properties one can use because every evaluation map lies in a neighborhood of diagonal. And you read this Costello's book about this perturbative Chern-Simons. And his construction, I think you kind of prove some kind of uniqueness. You have kind of some system of these numbers so that its support is in these diagonals. Then it is unique, and it should be something coincide with what you did, right? So this implies that what we produce in this way exactly coincides to this perturbative Chern-Simons. And also, so this perturbative Chern-Simons in some particular case. But you can say that, here we don't use any functional analysis. You have this just M itself, constant maps. But this story, you can immediately generalize if you know a bit about the functional analysis and the pseudo-homework curve analysis. And you can generalize to any Lagrangian submanifold in symplectic manifold. So you can cook up this moduli space. So this is a kind of a leading order term of the moduli space, which is a constant map. You can include non-constant maps, and you have these similar systems. And you can do the same process to get the whole kind of quantum version of perturbative Chern-Simons theory. Okay. And as I said that, but in this, to that generalities, we need a bit more, because here we have these descriptions of each moduli space by just single orbifolds and single vector bundle and single sessions. And if you want to do this functional analysis, you can obtain similar pictures, but only locally. So here you consider this moduli space of pseudo-homework curves. You have similar descriptions by this triple, but it works only a neighborhood of each point of your moduli space. So a neighborhood of your moduli space, you can construct this kind of triple. That is I think goes back to Kuranish's work on deformation of complex structures 50 years ago. And that's Kuranish pictures. And something which is a bit more recent is we can group. There is a notion of coordinate change of this kind of local pictures. And so what we can do is just you have a kind of system of this kind of neighborhood at each point of the moduli space so that they are compatible Then we can work out the stories I just explained in the simple case in a complete general setting of this Coordinate structures, and you get system of this perturbation data, and you get system of operations among differential forms, and which satisfy this property, which is Stokes theorem and this Fubini type theorems. So in that way, you can do this pseudo-homologic curve business, and I believe that in that way, kind of almost most of the modular spaces, you can use the same techniques, and the output should be that you can usually kind of think the modular spaces, and you forget any mathematical details. You can kind of frankly think what is the boundary of this and what it should be looks like, and you write down this kind of formulas, and that formula should be rigorous rather immediately. So you don't need to work out kind of any artificial or ad hoc methods. You can do always that kind of things. So that kind of things I wanted to work. We are now kind of writing more and more details, and so I don't know how much we can use this as to quantum field theory, because this Chern-Simons is very very special. But something like this, to have this kind of singularity at diagonal and to regularize it and to make it completely consistent with kind of symmetry, you see a lot in a book, textbook of quantum field theory. So I don't know. I mean, if you can do this, for example, in a Yang-Mills theory or something like that. But if we can do this, then you may try to use this kind of techniques or quantum field theory. I don't know, but it's a kind of dream. Okay, I stop here. Thank you very much.
Maybe I missed something in the beginning.
AKZ?
Pardon?
What Chern-Simons not three dimensions? AKZ, yeah.
Yeah, so in that case, you have a kind of operations between differential forms. So in a usual three-dimensional Chern-Simons, you assume something like cohomology is 0. So in this way, you have a kind of operation between cohomologies. Yes, and you can do family versions, so that makes non-trivial. Yeah.
So when you say it's Chern-Simons, so what is the group?
Group. So here we can just use differential forms, but you can include this vector bands. Yeah. These are trivial, but yeah, you can include groups on M surfaces. Yeah.
Other question?
So you have your unions of fiber products.
Yeah.
So are those unions like plumbings?
I mean, you have this fiber product of 2, and they are glued in a kind of triple fiber product.
But it's like plumbing, that if you plumb vector bundles.
No, it's just a direct sum.
Fiber, and you.
Triple fiber. No, this is just manifold with corners.
Yeah, but then you get corners. So
Yeah.
The union is double foliated by big.
Yeah. There is something like a kind of, this set itself, boundary itself is not a manifold with corners, because so you can just kind of push back. So it's something, it's something, normalized. Yeah.
If you get the solution of the master equation, you produce some kind of cochain complex in cyclic homology. Like you
Yeah, that's exactly.
Yeah, can you do this like locally on the manifold? Produce like a factorization over that?
Locally on manifold means.
Locally on the 3 manifold.
Yeah, probably this is local. Yeah, because your perturbation just works on this on the diagonals. But
you have epsilon, epsilon maybe needs some kind of...
Yeah.
Can you describe actually axiomatic support?
Yes. Yeah. That's also what this related is. We are doing, and so Costello's appears. If you fix epsilons, you can just do this on a finite many stage. So you have to do this kind of inductive limit things. Yeah. And so the strategy is that you put the structures up to some level, and then you fix epsilons, and then you take this homotopy inductive limit. That I think is similar to what you appeared in your books, and then we do it also on infinity things. So that's always we need.
Yeah, actually I have not a question, but some kind of tangential remark. There was also a lot of these equations. But in the case we don't have corners, suppose in complex situation, we have 2 complex cycles intersect not transversal, it should be 0-dimensional, yeah? And then maybe in fact it's infinite dimensional, they have virtual dimension is 0, and then physics should give something depending on small parameters as well. And the naive idea just apply heat kernel with time epsilon, smooth, and then there's naive conjecture that you get smooth volume form, which will be concentrated in things, and make conjectures that will have limited distribution of the intersection.
Yeah, I think in physics,
It's a kind of interesting question in Kähler geometry, for example.
In algebraic geometry type situations or complex geometry type situations, you can still expect that when epsilon goes to 0, this kind of thing converges at least at the distributions. But I think in differential geometry situations, no. it's wilder.
Or
Yeah, so is there actually an axiom that describes what happens when you change epsilon? I mean,
Some behavior at
epsilon
epsilon,
version?
I mean, you can use this statement itself. You have epsilon 1, epsilon 2. These two things are kind of cobordant, satisfying all these systems. So this cobordism gives homotopy equivalence.
So you had this corner extension, and in the corner extension statement there was an equality at the double intersection.
Yes.
So should I be worried that that was an equality instead of just an isomorphism?
Yeah, actually, in this case, you have a kind of global pictures. We can make it exact equality, but in the actual Courant structure case, it is better to say it's isomorphism. And in that case, it's not codimension 2 corners. We have to arbitrary higher corners. And we wrote down this property precisely, but it's longer.
Sasha?
What was the reason for having your punctures on the boundary rather than in the interior of Riemann surfaces?
Oh, I mean, you can include interior boundary, interior also. You can just generalize the story. But the boundary is, I mean, we want to cook up these operations on a differential form on M itself. And if you put the interior, it's not so much natural because if you imagine the kind of pseudo-harmonic curve, then the boundary lies on Lagrangians. So you want to kind of construct operations on a differential form on Lagrangians. On the interior, you are supposed to put differential forms on an ambient simplex manifold. In this case, a cotangent bundle. So if you want to plug in something on M should be 0 sections. M should be Lagrangian submanifold. It's natural to put it for the boundary marked points. Because non-constant map case, it's a kind of. So, but of course, you can include interior. In that case, the story gives somehow you have a kind of two spaces, Lagrangian and ambient simplex manifold. You have operations, it's a kind of open-closed story.
So what if your triple system is some kind of group acting on it, such that section is like equivalent?
Yeah, I think we can do everything in equivalent way. You do it in equivalent cohomology. I didn't write it up, but I mean that's something interesting because in a case we have a kind of group actions on a manifold, we can try to do this in equivalent versions, and this part of the process I explained is not so much difficult to generalize. What is more difficult is to cook up that kind of structures. But that I think is one can do it.